Hello, this is Pat Hindle, editor at MicroWave Journal. It is my pleasure to welcome you to today's webinar on silicon germanium or CMOS, choosing the right technology when performance is the priority, presented by Simon Pruton, the product line director of high performance silicon germanium at GlobalFoundries. Before we begin the presentation, let me cover a few items on the On24 webinar platform. In the center of the screen, you will see a window containing the presentation. You may enlarge this to full screen to have a better view of the slides. The window on your screen labeled Resource List contains a copy of the presentation, which you can download at any time. This webinar is being recorded and will be available for replay within about an hour from when we conclude, allowing you to watch it again or recommend it to colleagues who are not able to join us for the live event. You will find a link to the recording in the events section of the MicroWave Journal website. If you have technical problems, please click on the yellow box with the question mark at the bottom of your screen. It will take you to a helpful user's guide. After the presentation, we will have time for questions. So if you'd like to ask a question, just type it into the Q&A box on your screen. With the increase in adoption of mmWave RF communications and near terabit speed optical communications, silicon germanium technologies are in greater demand today. What strengths does silicon germanium offer above RF CMOS or SOI technologies? This webinar will explore several different markets, including 5G communications, radar, LIDAR, optical communications, and high-speed copper interfaces to understand why they are increasingly adopting silicon germanium again. Today's presenter is Simon Pruton, who runs the silicon germanium product line within the RF business unit at GlobalFoundries. He has worked previously in a variety of roles at several high-performance analog semiconductor companies. He holds a bachelor's in science in electronic and electrical engineering from the University of Birmingham in England. So at this point, I will turn the presentation over to Simon.
Thank you, Pat, and I appreciate the opportunity to do this today. Thanks to everybody at MicroWave Journal. I'm going to talk today, as Pat mentioned, about silicon germanium and how it compares in certain application areas to CMOS, and why we're seeing today a resurgence, if you will, in the use of silicon germanium in the market. I think back, before I go into this, I think back to a big lesson that I learned many years ago when I was at National Semiconductor, which is, honestly, I'm not trying to sell you on CMOS, on SiGe, where CMOS will work. There are applications where if you can make CMOS work, you should use CMOS. So I'm not going to try to position this as SiGe as a panacea for all problems. I'm going to try to highlight a few areas where silicon germanium can really bring something to the table. And the lesson I learned when I was at National was in fast Ethernet, in 10100 Ethernet, which is a 2 or 3 decades old now as a lesson. But the folks at National, when I was there, were absolutely convinced that BiCMOS was the only way you could produce a fast Ethernet PHY, 100 megabit PHY. And there was a lot of dialogue inside the company by a certain group of engineers saying, no, I think this can be done in CMOS. They lost that argument. National did a next generation in BiCMOS. Broadcom brought a CMOS PHY to market and took the entire market over the space of about a year and a half. And so if you can use CMOS, my advice every time is use CMOS. But if there is a performance advantage to silicon germanium, then I'm going to try to highlight those today in the different markets that we talk to. If you look back over the history of silicon germanium, IBM was the original developer of BiCMOS silicon germanium chip technologies, with the first silicon germanium process being qualified right back in 1995. So long in the tooth, this is mature technology for sure. And the immediate first adopter of this technology at that point in time was cell phones. It got adapted into transceivers for cell phones extremely quickly. And they spent 7 or 8 years shipping very high volumes of transceivers into the cell phone business at that point. Around about the beginning of the last decade, in the 2000 timeframe, however, CMOS became a practical competitor for silicon germanium in that application, and it's reached a point relatively quickly where silicon germanium was squeezed out of handsets. And again, it's a perfect example where if you can do it in CMOS, and CMOS works well enough, you'd be crazy not to, and that's what the industry did. Over that period, IBM actually got very much involved in driving SOI CMOS technologies that have since been adopted in a very wide range of handsets. In fact, it's hard to pick up a handset today that doesn't have a chip in from GLOBALFOUNDRIES because of what IBM did in SOI over that period. And that's the green arrow that's shown along the bottom of here. But we continue to invest, and we continue to put new technologies, shrinking the nodes as we went forward and increasing the speed of the MPN over time, to the point where today what we're seeing is GLOBALFOUNDRIES, through the acquisition of IBM back in 2015, is very well positioned to participate in this rebirth that's going on of silicon germanium that I'm going to talk to in the presentation today. To the point where we've actually, as you see on the far right of this chart, we're transferring our highest performance 90 nanometer node into 300 millimeter technology, which, as I talk on the next slide, is one of the places where CMOS typically has been differentiated over time. So this shows at a very high level, before I dive into application details, this shows where SiGe excels. And I'm going to come back time and time again through this presentation and talk to these again. But really, if you look at this at a high level, it really comes down to a handful of different things. The first two lines really are an indication of the speed of the silicon germanium processes. And the fastest process that we have in production today runs about 320 gigahertz for the FT and shows an Fmax on the MPN of 370 gigahertz. So that is kind of the industry's leading edge performance point for silicon germanium technology today. But there have been demonstrations well in excess of that, running up to 500 gig FTs and 700 gig Fmax, significantly outstripping anything that can be done in CMOS. Those are not necessarily, however, production technologies that can be done in high volume, produced in high volume, but it reflects the latent potential, if you will, associated with silicon germanium moving forward. The third line on here shows breakdown voltage, and just through by definition, essentially through the way we build these MPNs, they're going to be better for breakdown than bulk CMOS. There are tricks that you can play with SOI technologies, which we talked to in webinars in the past, where you can stack transistors to achieve higher breakdown, but it's a lot harder to get there than just selecting a bipolar device in a silicon germanium process and get access to that raw breakdown capability. Next is 1 over F noise, which is going to turn up in a couple of the applications I talked to as a key differentiator for silicon germanium, where again, just simply through the physics of these devices, you get something like 100x better 1 over F noise than you will from CMOS, and that's pretty much any CMOS technology. So that's a major differentiator in some of the applications I talk about as I go forward. The two areas where CMOS has been successful historically, the first one is it allows greater integration. If you have a high degree of digital content, then CMOS is going to be the place to try to take it if you can. And then secondly, wafer size. Traditionally, RF CMOS has been a 300 millimeter technology. Most of the silicon germanium foundries in the world run 200 millimeter today. But as I say, that's one advantage that we're going to pull even with CMOS on next year as we release our 90 nanometer SiGe 9HP process into 300 millimeter in East Fishkill, New York. And then the last one is mask cost. And this is an interesting one because if you look at the chart on the right, you can see for any given FT point, you can look significantly off to the right for the SiGe node. And you are 2 or 3 generations more mature as a node, which gives you lower mask cost. It gives you more proven technology than you have to use necessarily in CMOS, which makes in general for a more predictable outcome on your first silicon. And you can see those two lines have, to some degree, moved together more as you move up the FT curve to the point where 90 nanometer shows. That's really by benefit of the fact that I've shown the geometries on the bottom. I've shown on a linear scale. There were still 2 or 3 generations of CMOS technology between 90 nanometer and the 28 nanometer that's shown at around about 300 gig FTs. So you're still trailing behind by 3 nodes essentially on the SiGe technology to achieve a similar level of performance. But as I said, if you have a huge digital block, and you have the need for significant integration, then CMOS could well be the way to go in some applications. So I'm going to talk now about several different applications. The first one I'm going to talk about is 5G and phased arrays, and then I'm going to talk about automotive radar and gesture sensing systems, and then LIDAR systems, which are a relatively new addition to the users of silicon germanium technology, just by nature of the age of that system and the newness to the market. And then I'm going to talk briefly about high-speed optical communications, and I'm going to spend a lot more time on the 5G phased array and automotive radar systems up front, because I feel there's probably a better match with the audience of a journal like Microwave Journal. There's a better match with what you're looking for. And we simply don't have enough time to go into all of them in the same level of detail. So I'm going to talk first about 5G and phased arrays communications. And you'll see if you're reading this magazine at all, you'll see phased arrays are pretty much everywhere. And the first thing that you'll note is it isn't one application. You can see 5G, and 5G is for 5G millimeter wave technologies, which will be rolling out over the next 5-6 years. 5Gs are probably the most discussed area of millimeter wave phased arrays, but backhaul in cellular infrastructure has already been shipping for some time. So that is ahead of the actual voice channel, data channel to the phone in terms of its use. And we have many customers who are already designing in millimeter wave backhaul systems today. Automotive radar systems have been using phased arrays again for years. Showed up first as luxury items in cars. Really no longer the case today. It has been being adopted in a lot more vehicles today than it was historically with the advent of driverless vehicles. And then low Earth orbit satellites for broadband communications again have traditionally not used phased arrays, but just about every development that's going on in this area today is adopting phased arrays going forward. And then finally at the top there you've got Wi-Fi, or really as it was known before until it was rolled into the Wi-Fi family, WiGig, which again is 60 gigahertz millimeter wave phased array technology, delivering higher performance Wi-Fi standard for applications where you need to transmit video over the air at very high resolution. So a lot of different areas adopting phased arrays as the market moves forward. So exciting areas. But the first thing to note when you're looking at these phased arrays is almost across the board they're adopting new modulation techniques. The OFDM is the most common of these. That is modulating the signal in a far more complex way, and as a result requires a level of linearity from the devices designed than simpler modulation schemes called for historically. OFDM requires that you think about the most likely operating power at any point in time, but you also have to take into account the peak operating power that you're going to have to drive, and you really have to then look at typically you select a power amp that is biased for its max power required at the 1 dB compression point, but you won't be operating there. You'll be operating at a backed off level, which could be as much as 10 dB backed off, which is really what this top chart is showing here. You're not going to be, you have to choose a power amp, you have to design a power amp that's going to handle that peak power, but that's not necessarily where you're most likely to be operating most of the time given the standard. So you have to have a PAE, which, by the way, is really a simple way to capture the efficiency of a power amp that takes into account the gain of the power amp as well as driving in a low gain mode is obviously going to consume more power in the driving stage, so it takes that into account. But you can see from the chart below, which I'm going to come back to later in the presentation, you can see from the chart below how some of the typical power amps that are out there are optimized. And you can see how much the PAE is much lower when backed off by just 7 dB, which is shown in this example. The second thing that you need to worry about is losses. In millimeter wave, any of you who have gotten involved in millimeter wave are going to know this already. It's almost RF 101. But if you think losses at 5 gig is tough, the impact of working at 28 gig or 39 gig or 60 gig even is just a downhill fight. The higher you go, the more easy it is for your signal to get attenuated by the slightest bump in the road. You can no longer necessarily afford to drive an external power amp. You'd really rather keep what you can on chip. So it drives integration considerations that were not necessarily as critical in system design earlier on. And smaller arrays drive a need for much greater power levels. Larger arrays can help, for sure. And I'm going to talk about that more in the next few slides. But you can't always afford the duplication that drives. You can't always fit a larger array into the form factor that you need to target. And I'll talk about that a little more over the next few slides. So what I'm showing here, and I apologize, there's supposed to be a formula with values at the bottom of this slide, but as we reformatted the slides to use this ON24 system, the formula got dropped. But what it's essentially showing in this formula is in any phased array, the power output is generally expressed as an EIRP, equivalent isotropically radiated power, which is the product of transmitter power and the antenna gain in a given direction, compared to a conventional isotropic antenna. And you can calculate using the equation below the EIRP, which is not showing, I guess, up on your slide. You can calculate from the number of array elements, the total gain of each element, the total power output by the array. You can calculate the EIRP. Now, the total power output from the array is influenced by the amount of power that you're having to drive into the array, multiplied by the efficiency of the array itself. And so you can ultimately come up with an equation that allows you to plot the lines shown on this curve. And it allows you to plot the number of elements in an array against the power required to drive the array. For a given EIRP and element gain, you get an array of lines linked to each efficiency value that you insert into this equation. And the PDF for this presentation online, it includes that equation. So you can download that if you're interested in getting the detail on this offline. So what I'm showing here is actually an EIRP of 30 dBm. So it's a 1 watt power amp and an element gain of 3 dB. And just using this equation, you can set up these lines. So assuming that you have to work at a 600 milliwatts total power, you can see where that line, 600 milliwatts, which is marked in the black line on this curve with the 2 green stars on it, you can see where that line crosses the chart in terms of the number of elements you need in order to achieve the IRP goal with 3 dB gain elements. So you can see for 8 elements here on the left-hand star, you can see that's going to require you to be at a 10% efficiency. If you can only manage 2% efficiency, you're going to need to throw a 40-element array at this. And that, as I said before, that in a lot of applications is simply not an option. If you look at a handheld application, for instance, it is really not an option to put a 40-element array into a handheld device. It simply becomes too complex. And it also becomes a challenge to manage the losses associated with that as you move forward as well. So same thing on this slide. There is actually the formula is missing again, and I apologize for that. But again, if you take the same example for a 600 milliwatt power limit delivering a 1 watt output power, you can very quickly work through the calculations to understand first the transmitted power per element, and then the 1 dP power level required to drive each element at back off, selected again at 7 dB in this case. The continual trade-off to be made is whether or not you can afford that bigger array in your system, as this example clearly shows the number of PAs significantly increasing. Or another way to look at this is that the power required to achieve a given level of performance can be reduced by 5x if you can achieve a more efficient power amplifier scheme. In a small battery-powered application, as I was saying just now, the combination of the power drawn from the battery and the heat generated by an inefficient PA have essentially eliminated RF CMOS for consideration in handheld systems for phased arrays. The two contenders today are SOI CMOS and silicon germanium. And silicon germanium is bringing performance levels to the market that leave SOI standing. Now, I don't want to talk in each case to what we've done or what GLOBALFOUNDRIES throws out there as a benchmark. I want to try to share in most of these cases, and this being the first example, some work done at universities to show what is possible. So this is showing what the folks at NC State published middle of last year, about 9 months ago, utilizing state-of-the-art power combining techniques to achieve power levels that are unmatchable in any other technology today, essentially. And what SiGe brings to the table to do this, it's probably possible with a lot of tweaking. Honestly, it's probably possible to get close to this in SOI technologies, but so far the academic work going on is showing that SiGe brings a significant advantage to the table in terms of efficiency at back off, and just raw output power at those efficiency levels. So it's a combination that allows you to move towards the smaller arrays that we talked about before, allows you to move towards those smaller arrays and achieve a operation in a performance and form factor envelope as demanded by the market for some of these technologies moving forward. So what is it that SiGe's doing that makes this possible? Because that's ultimately is what I want to try to boil this down to as a slide in each case and a clear message. And it breaks out in this case, in this power amp case for phased arrays, it breaks out really into three things that SiGe does significantly better. And some of them are obvious, and some of them are a little less obvious. And some of them, until I was pulling this presentation together, I hadn't actually realized the magnitude of the benefits. But the first one, and it's a big one, is the breakdown voltage. If you want to drive power, you clearly have to be able to deliver high current at some reasonable voltage level. And SiGe is, to put it bluntly, it's simply better at this by the physics of the matter. The BVCER of bipolars, the avalanche breakdown, if you will, also enables extremely simple 50 ohm output impedance. So you get the ability to drive current, voltage, and you don't have to build fancy matching schemes in order to allow power combiners compared to CMOS, where because of just the very nature of the higher impedance of CMOS, you get driven to use matching networks where, again, you start to see losses, you start to see efficiency losses as well. The second bullet here is higher current density. And if you look at the chart on the right, the black and white chart on the right, what this is showing is work done at the University of Toronto, where they compared the the Fmax, and noise figures for a 130 nanometer NPN and a 65 nanometer CMOS device, well, an MMOS device in this case. And each parameter is plotted against current density on the bottom. And you can see the top two curves, the one with the gray squares, that is the 65 nanometer technology, Fmax, and the one with the black dots on is the Fmax for the SiGe. And you can see a significantly higher current density capability from these devices. If you look at the two curves underneath that with the white circles and the white squares, you can see again the same thing is true for FT. The peak performance is at a much higher power density in silicon germanium than it is in CMOS. And you might see you might immediately think, gee, this is 65 nanometers, and that is hardly state of the art. But this doesn't improve. This is not one of the factors that improves with smaller geometries. In fact, to some degree, it can get worse unless you're really designing the process and optimizing the process for this. And then the other two curves at the bottom that are the inverted shape, that's the noise figure. And again, the noise figure is peaking in terms of its lowest number at a significantly higher current density for SiGe here than it is for CMOS. And that turns into, especially those two speed factors, turns into a higher output power. I mean, if you can achieve higher voltage and higher current density, you are going to be able to build a better power amp, pretty much, period. And then the other piece of information that's shown at the bottom on here in the third bullet is the one that I said is maybe less obvious, and that's the interaction with the metal stack itself between a CMOS device and a bipolar device. FETs, because of their physics, again, because of the basic way you build FETs and the basic physics of how you build an NPN, they're more sensitive to the parasitics in the stack. And this is some data that was taken by where did this come from? I forget. I think it was NC State again, where they compared what the FT and Fmax, and I'm showing Fmax here, what the Fmax did when compared on metal 1 at the bottom layer of the metal stack versus the final layer at the top level of the stack. And silicon germanium, because of its ability again to drive the stack and its the physics and impedances of the collector, is able to drive the stack significantly better. And again, this is not my data. This is data generated by NC State, but you can see the raw CMOS speed that you can see when you're looking at the bottom level at metal 1 is equivalent to silicon germanium. But once you get to the top of the stack, silicon germanium has attenuated marginally, but CMOS has cratered. And that turns out to be a bigger deal than you might expect. You try to avoid coming all the way up and down the stack multiple times in your design, clearly. But you can't avoid the stack altogether, and at some point to get out to the real world, you have to come to top level. So you have to come up to the top level at least once, and in order to route signals, the reality is you have to get up and down into those thinner first 2 or 3 metal layers on a frequent basis, just in order to route signals around on the chip. And so as you go up multiple times, the combined impact of that becomes such that you can no longer rely on getting the FT measured in the CMOS process. And as I say, it's less obvious. This isn't one that I had actually thought about too much until talking to some of my colleagues in preparation for this webinar. But it's a remarkable advantage that silicon germanium has over CMOS, again, just through the basic structure of these devices. So that's really what I wanted to say. Those are the 3 items that really allow the work that's being done today at universities and at some of our customers to build a better power amp for phased array systems. And with that, I want to transition over to radar and talk a little bit about automotive radar. This is still phased arrays, but really it's a completely different application of the same kind of technology. What is happening today in driverless vehicles is there's a fight going on between 2 technologies. One is radar, and the other is LIDAR. And in driverless cars, you really want to know what is 200 or 300 meters ahead of you in the vehicle. What, in terms of the long range ahead, is walking out into the road or happening in the road ahead of you that you need to react to. So if you spend any time looking at the automotive market today, you'll see that radar has been adopted in a large number of vehicles today, an increasing number of vehicles. Started off as a luxury item in the automotive segment, but is now turning up more and more in a very wide variety of vehicles. It was first an option in vehicles. It's now become standard in luxury vehicles, and it's an option in lower end and mid-range vehicles. However, radar while it does great at detecting a car ahead of you, and it will warn you of a car braking early, and you can combine some of the camera-based technologies that are turning up in cars today to help build this image. LIDAR today is actually being deployed in every driverless car except one company, Tesla, who are being vocal on the record that LIDAR is not necessary in driverless cars, and I frankly wonder how long it'll be before they back away from that, because I think that day is probably coming as well. But LIDAR, and I'll talk about LIDAR in the next section in more detail, LIDAR builds a far more detailed 3D picture of the environment that allows you to see exactly what is ahead. You can see the direction a pedestrian is walking across the road very, very easily with LIDAR, and as a result, LIDAR is being deployed into into every autonomous vehicle, as I say, bar the ones being worked on by Tesla today. So the radar manufacturers are all doubling down on radar, as you would expect, and trying to improve the capabilities of their systems, and that's not an unlikely thing to happen, because if you look at military radar systems today, they are far more sophisticated in terms of what is possible and what has been done in automotive radar so far. There are already 3D imaging radar systems out there that have been used extensively for military applications. And so the automotive market is both trying to get radar to up its game and to try to drive LIDAR to drive its costs down. And one of these guys is going to win long term, but it's I think for the time being, both of these systems are going to operate. They're going to coexist in both driverless vehicles and relatively autonomous vehicles where there's a very high degree of driver assist available. So in terms of radar, modern radars are no longer time-of-flight based and haven't been for years, but rather they're broadcasting a continuous frequency modulated signal, the majority of which today is in the 80 gig area, around about 78 gigahertz area in the world. There have been some 24 and 27 gig radars in the past, but for the long range, high power area, the world is coalescing really around a 78 gig area. And the targets captured by the radar reflect that signal back to the originating transducer, where the phase and frequency are analyzed. And there is a significant amount of DSP that then goes into building an image from that data. So you see on the bottom here, because I pasted an image of this equation, it transferred across just fine. But a gentleman by the name of Leeson brought out David Leeson brought out generated a formula decades ago now that has been maybe improved upon a little bit over time by various work that's been done. But it describes, the oscillator's phase noise spectrum and provides the basis to allow that DSP, that FFT processing to be done to build an image. So, as I said, a lot of people have kind of improved on Leeson's work over time, but his was a lot of the founding work that went into building this radar technique. And the folks at Friedrich Alexander University in Germany did some work just a couple of years ago to analyze what are the things in Leeson's equation, and they did a huge amount of simulation work to work their way through this. What are the things in this equation that really move the needle on the quality of the system? And what I've highlighted in their conclusion that I just pulled straight out of this paper, which you can download online and go through the detail of which there's much in their paper. And they said a simulated two-target scenario showed the importance of a high-quality oscillator with a little phase noise, with as little phase noise as possible. And that ultimately is why for almost every shipping unit today of automotive radar, they're using a bipolar technology, a silicon germanium technology today. And that's not to say, on the long-range side, that's not to say this can't be done in CMOS. As I said when I came back, it is that as you look for higher resolution and higher performance from these systems, and you try to compete with LIDAR-type applications, and you're trying to improve the resolution at great distance, you need to focus on the sources of error in these systems. And so phase noise ends up being the one that dominates this equation. And to demonstrate this, I'm showing you a curve here that was again presented last year by Vadim from Infineon, Vadim Isakov from Infineon, where he was actually not in this case building an automotive radar, but it's data that I had access to. And the same thing is true for what all of the automotive companies are doing from a radar point of view. This is actually for a gesture sensing radar, where today there is an adoption in the market of mmWave radar technology for detecting gestures in front of consumer electronics. And this is something that the likes of Google are pushing extremely hard today. And I'm expecting that they will be providing some updates this week at Google I/O to show what is possible from a gesture sensing radar point of view to allow you to control electronics without touching it. Will be, I think, especially interesting for automotive systems where you mount a phone on the dash and you still want to interact with your phone through simple gestures rather than reaching all the way over to the phone and trying to manipulate the screen. So this curve shows a SiGe device and actually a device that was built in another GlobalFoundries technology, a 45RF SOI technology, our leading edge mmWave SOI technology. And it shows the straight advantage to the 15 to 20 dBc per hertz of phase noise that is offered. And that turns into a huge advantage in these systems in the field. The 1/F performance in silicon germanium that I mentioned that is at least 10x, if not 100x better than CMOS technologies, translates directly into improved phase noise in the VCO. And that is why, as I say, there has been a move over the last few years to try to move radar to CMOS. And if you'd asked the industry 2 years ago, where's auto radar going to be in 2 years, you'd have heard the answer. It is going to be in CMOS across the board for every application, automotive radar, because of the cost implications of digital integration into CMOS nodes. However, that long range, that radar on the front of the car looking at 200 meters, has by and large not moved to CMOS for this exact reason. And as the performance requirements to take on LIDAR and displace LIDAR, and I do believe that probably radar, has a leadership position to displace LIDAR from cars 10 years from now, because of the things that I think are being brought to market. I think the only way it stays there, the only way it is able to stay there, is through continued use of silicon germanium. And I would say, to address the second bullet on this chart as well, the other thing is this is still a phased array. So everything I said in the last section about phased array power amps, that's still true here as well. You still have higher efficiency. You still have the ability to build a better power amp. You still have the ability to project power forward from the vehicle more efficiently than you could with a CMOS technology. But it isn't that truly differentiated in this application. It's the 1/F noise that does that. So that's really all I want to say about radar. I'm going to talk a little more about LIDAR now. But as I say, for these last couple of applications, I'm going to say a little bit less. I think it's to some degree it's repetitive in terms of some of what is attractive in SiGe. So I'm going to try to cover this a little more quickly so that we can get done in time and leave some time for questions. So LIDAR is not dissimilar to radar in some respects. It projects lasers from a laser source on the front of the vehicle, or in the case of some of the autonomous vehicles you see driving around today, on the top of the vehicle, the domes you see on top of a Google a Waymo, I guess, driverless vehicle, is a LIDAR. And in the case of the domes that sit on top of a vehicle, they are a rotating device with a mirror inside that rotates an array of lasers around to build a picture of the environment. The light pulses reflect back to a photo detector on the vehicle, and that time of flight of that signal allows you to calculate the distance from the object that you've detected ahead. So relatively simple, doesn't require the degree of DSP processing in order to build a reasonable image that I'll show you on the next slide in just one moment, but costs significantly more than radar today. And the cost of those rotating domes on the top of some of the vehicles you see driving around in certainly Silicon Valley today those are tens of thousands of dollars. They are in many cases more expensive than the car itself. And that's clearly not a viable model going forward for automotive companies to double the price of their car to make it autonomous. So the number one focus in the LIDAR market today is to drive cost out of these systems and to move towards solid state systems that eliminate the mirrors, simplify the optics, integrate the electronics, because the early systems had no essential integration at all. They were using off-the-shelf components to build the systems. But now there's a huge focus on how can we cost reduce this, how can we make this a viable option for automotive suppliers going forward. So this slide I've only included. I'm not going to talk to it for long. This slide shows you the raw output from a LIDAR sensor without any image processing, just looking at the time of flight data and the position of the mirror as it was turning on top of the car. You can immediately start to see the quality of the data that comes back from this. And you move the car forward an inch, and you're going to fill in the black gaps. So that is why you get better image quality, better image data from LIDAR. It is why the autonomous vehicle companies are all looking at LIDAR as a technology, because in order to build an image of this quality takes an enormous amount of horsepower in radar. Takes a FinFET technology type device in order to integrate significant graphics horsepower to build an image equivalent to this from the radar data that is available. And again, that's not to say that the radar guys can't do it. I think they can. But LIDAR makes it easy to get access to this in time frame, in an immediate time frame. And that's why this technology has been favored by all the automotive guys, and you're seeing it show up in pretty much all of the devices that all the driverless cars that are out there. So the challenge associated with this system is acquiring and digitizing that laser pulse that bounces back. In the event that the target is 200 meters away and non-reflective in nature, you are not going to get a lot of light coming back to the photodetector. They typically use avalanche photodiodes on the front end of these. The highest gain photodiodes you can get. They're typically operating, most of the systems shipping today at 900 nanometers. But the photons coming back mean that the current from this TIA on the front end of the receiver is tiny. It's going to be measured in nanoamps. However, if a bicycle crosses the road in front of you, this system needs to immediately go from a situation where it's receiving just a few photons back to receiving tens of thousands or hundreds of thousands of photons back. And it needs to immediately respond to that transient change and capture at the first opportunity the fact that there's a bicycle crossing the road in front of you so that the vehicle can brake. And that is really the challenge associated with this application. The two factors that play into it are, one, noise. You have to be able to pull those few photons. In the few photon example, you have to be able to pull a signal out of the noise. And so we're getting requests from some customers for improvements to some of our processes for 1/RF noise. But in addition to that, you need very, very fast transient response from the rest of the system in order to be able to make sure that when that bike comes out in front of you, the system knows immediately that's a bike right in front of you, you need to stop. And so those are the two factors that drive this system. The 1/F noise, again, that I've talked about before, which is 100 times better than CMOS systems, and very, very fast transient response so that you can immediately react and capture accurately the fact that there's something potentially highly reflective and close to the vehicle in front of you, so you could swerve or brake or whatever you have to do. And really today, only silicon germanium can achieve the required specs that are out there in terms of being able to pull that signal out of the noise and respond quickly. You can certainly implement this system in CMOS again, but you don't achieve the same level of sensitivity as you do in silicon germanium. And that, for the majority of the market today, has proven to be a showstopper. We have customers today that we're talking to who have designed in CMOS and stopped, backed off, and gone and redesigned in silicon germanium. So I said that there's a focus in this market more than almost any other market I can point at on cost reduction. And so the desire was to try to use CMOS out of the chute for many of these guys, but that has not stuck. And most of the customers who have looked at trying to use CMOS that we're aware of have either decided to live and go after a different part of the market, or have had to move back to silicon germanium in order to make this work. So it's going to be interesting to see over the next 5-10 years how this plays out in the market. There is, without any question, there's a battle going on between LIDAR and radar. To a degree, I don't mind who wins, because both of them seem to be using silicon germanium technologies. So I have a dog in this fight pretty much either way it goes. But at this point, I couldn't really forecast which way it's going to go. Both camps are moving very aggressively to meet the goals of their end customers. I think it's going to be very interesting to watch how it plays out over the next 10 years. So the final area I'm going to talk about today, and I'm conscious that I'm using up time real quick. I think we've probably only got 10 minutes left, so it should still leave some time for some questions. But the final area I want to talk to today is optical communications. And this is one of those markets that has consistently used silicon germanium over the last decade or two from implementing high-speed electronics. And again, it's for the same basic reason as I just talked about in LIDAR. There is a signal coming over the fiber that is extremely low and needs to be pulled out of the noise. And you're trying to drive at speed as well. So you need a combination of speed and noise in these systems. But what keeps these applications silicon germanium instead of CMOS technologies, again, aside from that, is the speed at which the market is moving. So I mean, this block diagram, and again, I'm not going to cruise into the details of the interface or the PAM encoding, but the biggest thing that's happening in the data center market today is the move from 10 gig Ethernet to 25 to 40 to 100 gig to 400 gig. It's happening significantly faster than anybody forecasted, all driven by the move to the cloud of all of our data and the significant increase in the amount of data that we're all pushing to the cloud. It's not just photos, it's not just videos. The LIDAR application and radar application that I showed just now, in order to make the road safer for us long term, all of that data will get pushed to the cloud as well, shared with other vehicles in your vicinity, so that you can start to benefit from the radar system on one car to improve the safety in another vehicle. So you can see essentially around corners with some of these systems and improve safety further. So in order to accommodate that load on data centers, the rate of communication between servers, between server racks, and between data centers has been driving just exponentially over the last few years. Just a few years ago, 25 gig was state of the art. 400 gig optical modules are sampling today into a wide variety of these applications. Some just going a few meters over cheaper fiber. Some being set up to connect data centers, so you can keep data centers synced up and keep data local for all users. And the growth, as I say, continues to be explosive. So as I said, silicon germanium has been used by this market for years. The majority of players in the vast majority, in fact, I think pretty much all the players in the optical marketplace have used silicon germanium. Even companies who have prided themselves on the adoption of CMOS for other networking applications have continued to rely on silicon germanium, especially for the transimpedance amplifiers and laser drivers. And there's often a retiming element that's included on these devices, those devices as well. they've traditionally stuck with silicon germanium, and as we're moving forward, the simple NRZ signaling is proving again to be insufficient to drive the data rate where it needs to go. And this is the same parallel, if you will, to the use of OFDM in 5G. What the optical guys are using is PAM4 signaling. And if you look at the IEEE 802.3 BM standard that was made available for 40 gig Ethernet and 100 gig Ethernet, it had a PAM4 element to it. So PAM4 was essentially an optional part of that standard. As they moved to 400 gig, the only way you can get that much data down a fiber or a number of fibers is to adopt PAM4 across the board. So PAM4 was adopted as a mandatory standard for 400 gig Ethernet. And what that does, in exactly the same way as we talked about on the linearity requirements for a power amp, what that does is it drives the need for better linearity and essentially more speed. You want to stay away from the FT and have a bigger multiplier between the speed of the circuits you're designing and the FT of the process. And that drives the need for higher performance SiGe. And when you combine that with what I showed you on the top metal versus bottom metal before, it puts another strong check mark in SiGe, because in this market, if you look at this market over the last few years, although there are a vast number of competitors in this market and startups appearing in this market over time, to the point where there are 20 or 30 companies running after, the prize in this market at each node, at each speed node. What you see is 3 or 4 guys make a lot of money from this market. 3 or 4 guys who get to market first make the money in this market. So that is the other element that is the reason really why SiGe has been used over time in this market, is because there is a time to market advantage, and you cannot afford in this market, when you're moving from 100 gig devices to 400 gig, you almost can't afford to reinvent the wheel. There isn't time. When I look at Light Countings, who are one of the market companies that track this market, when I look at their reports, and they are, in my opinion, the best reporter of the optical module business, they have essentially missed the market by half in successive forecasts that they've put out there, because of the speed at which this is growing, because the end customers, the Googles, the Amazons, the big data center companies worldwide, they keep on pulling in their needs. They keep on accelerating the ramp up of these new nodes. So 400 gig is what's shipping in as sampling today into all these markets, and all of these companies are now starting to move on to terabit type speeds. And as a result of that, you can't afford to go back. You can't afford to miss the target on first silicon, and you can't afford to go back and start over from the point of view of your IP. So the market rate of change also drives a need for silicon germanium in this case as well. So those are the 4 markets that I wanted to talk about and touch upon and try to explain to you where the silicon germanium technology is adding value. But I'd be remiss in not talking at least somewhat to the GlobalFoundries technology platform that we address this market with today. We have, and I'm not going to spend a ton of time on this slide, but we have essentially the highest performance MPNs in production in the world, with Fmax of 370 gigahertz. We have, in each case, we deliver, in addition to just the raw speed of that highest performance MPN in a process, we deliver a suite of auxiliary bipolar devices. The trade-off on the speed, the FTs of the devices themselves, to deliver a higher breakdown device, or in some of our processes, a complementary vertical PMP type structure. We have a copper backend that we developed specifically for this technology, which allows you to drive more current in the thin metal layers at the bottom of the stack without running into electromigration problems. So that's just another example of how it isn't just about the MPN. It's about looking at the holistic solution that we're bringing to market with our silicon germanium technologies, and making sure that we don't put a bottleneck in the stack to accessing the raw speed of the technologies that we're selling. And then comprehensive RF support through all the passive devices that we ship, mmWave modeled transmission lines and the like, through silicon vias to allow backside grounding very simply in some of these systems. Fully characterized FETs for RF, which is a feature of all of our RF technologies, be it CMOS or the silicon germanium technologies. And finally, full and complete DC and AC model-to-bench correlation. The documentation that we bring to market, I think, is again one of the things that I consistently get feedback on as an area where the IBM approach over time, and now the GlobalFoundries approach, because we've since we bought the IBM technologies in-house a few years ago, the way in which we document and model the model-to-bench correlation is I think almost unparalleled in the market today. And the degree of documentation, we have a model reference guide for each of these technologies that is to the tune of about 500 pages long in most cases, showing every single parameter you could dream up pretty much, and how measured data compares to what's in the model. And if the data that you want and the cut that you want isn't in that data, we've got engineers who are available in order to build a fresh cut of that data to be able to satisfy those applications. Complete analog digital support. Clearly, we bring to market a wide variety of CMOS nodes for digital integration of these technologies, and we bring in each of these standard cell digital libraries so that you can do logic integration as well, I/O libraries, eFuse, etc. And then finally on here, world-class manufacturing. And I mentioned this before. All of these technologies that I've talked about today, by and large, are produced at 200 millimeters a day in production volumes. We're bringing up our first 300 millimeter silicon germanium line in 2019. And again, it takes away from CMOS one of those claims to fame that CMOS has had for years, which is, yeah, but SiGe's 200 millimeter, you don't get the economies that 300 millimeter brings to the market. That changes as of next year with GlobalFoundries taking our 9HB process technology into 300 millimeter. So in summary, IBM, who GlobalFoundries have integrated into our DNA at this point, IBM invented this technology 25 years ago. But really, we're really only just getting started from the point of view of this. We have a roadmap of technologies laid out to further improve the MPN speed and the CMOS density, so that we can continue to drive differentiation in these products and continue to deliver more and more value and allow the creation of systems that CMOS simply doesn't allow you to engage on. I'm not going to touch on this slide at all. It's in the deck for your use if you want access to it. It's in some of our other literature on the web as well, but gives you some idea of the capability we have. You can see the FT scaling up as the node on the top line moves from 180 to 90. The speed of the MPNs going up from 60 gig FT to 300 gig FT. So continued improvement there is what our roadmap essentially is all about. And as I said, as I talked to that couple of slides back, it isn't just about the process. It's about the models. It's about the design support that we bring to market. It's about packaging support. We also provide a broad range of packaging, test, and design services to market, which again are, relatively speaking, I think are unmatched in the industry today. We have the ability to do wafer test and final product test in our factories in a factory in Burlington, and and offshore as well to some degree, we have the ability to test up to 90 gig millimeter wave, as I say, at wafer test. So I don't know that you can point to any other wafer foundry that has that capability, but we have the ability to therefore deliver a turnkey solution that gets you the wafer manufacturing, gets you into production, gets you a tested unit that is shipped and put into your hands. You no longer have to go out and try to figure out how am I gonna work on the back end test of this. We'll take care of that problem for you. We have hundreds of years of experienced engineers waiting to help. So we have a complete suite of services that we bring to market here. I'm talking more about the SiGe technology today, but we bring a much bigger platform to market than just that. And I wanted to end, though, on again, coming back to what I said at the beginning. I don't want this to be about what GlobalFoundries is saying that SiGe is good for, because ultimately, you know, you should maintain a healthy level of skepticism about our motivations to position this technology. So I wanted to finish with a slide from John Kressler, who is a professor at Georgia Institute of Technology. And I wanted to leave you with his thoughts on silicon germanium. And I don't think there's anything on this slide that I haven't already touched upon. You know, his take in this first bullet is that if cost were no object, 3.5 devices would always dominate. CMOS is a great technology, but it doesn't always get you to the end goal. It doesn't always allow you to reach the performance levels that you want to reach. Silicon germanium BiCMOS technologies are a middle ground that allows you to almost put one foot into each of those worlds. And he's listed out some of the key advantages here. And again, I've talked to all of these to some degree already. For equal performance, silicon germanium requires a less aggressive node. That node translates directly into a mask cost advantage. 130 nanometer SiGe, he's calling out here, costs significantly less for a mask set than 65 nanometer CMOS. So the NREs associated with entering and getting to the point where you've got a design working are significantly lower. And as CMOS costs at 28 and 22 and 14 nanometer go, you know, way into the millions of dollars, that actually is becoming a bigger and bigger concern for many of our customers. If you have a business that doesn't run cell phone type volumes, it's getting harder and harder to justify the expense associated with the tape out into these leading edge nodes. And again, by using less aggressive lithography, we don't require you to drive to the same level of expense in terms of our NRE while delivering equivalent performance. He talks about breakdown voltages, which I think I covered as I went through. He talks about the fact that those breakdown voltages allow you to generate more power at a fixed frequency, which I think I've covered in some detail. He's talking about the GM per micron squared. It's much larger for silicon HBTs. You need big NFETs to match this. Match silicon germanium's capabilities there. The 1/F, as I've mentioned a few times, 100 times lower. Silicon germanium HBTs, the output conductance, this is what I mentioned a couple of times, makes it much easier to predict how they're going to interact, how they're going to work in your design. He then mentioned something that I didn't really talk to in here because I didn't talk about military applications or space applications at all. And that is that silicon germanium HBTs also have a built-in total dose radiation hardness for those applications. So something I didn't really touch about as I talked through. So it makes them, you know, a natural choice for more and more applications today as CMOS becomes, you know, more and more expensive. But again, I do want to say that if you can use CMOS, you'd be crazy not to. But if you see an opportunity for silicon germanium at a more conservative node, it can often be that it's a better match in an application today than aggressively scaled CMOS is. And again, that's not my opinion. That's John Kressler's opinion. he's a smarter guy than me by a significant margin, and that's why I wanted to finish with a slide like this. But that, as I say, that's the final slide I had in the deck today. I do want to thank again Microwave Journal for letting me run through this today. And at this point, I'll hand back to Pat for questions.
Okay, thank you very much for a great presentation, Simon. If you have a question, enter in the Q&A box. We'll just try to take one or two quick questions since we're a few minutes over here. Can you, on the same subject you were ending on there, can you compare the cost of SiGe versus CMOS?
So that's maybe a predictable question. If you look at the steps required to add an MPN to a process, to a CMOS process, it is something in the range, and this varies by node, but it's something in the range of 10 to 15 steps. So it's masking steps. And so if you assume that a base CMOS process has something in the 20 to 22, 23 steps in order to build a similar stack, you're essentially adding a significant amount in terms of wafer cost. You are adding a significant amount of cost to the equation. However, in order to match, again, it's not apples to apples, because in order to match the performance in CMOS, you're having to use a more aggressive node, and that generally removes the majority of the cost adder. It certainly doesn't remove it completely, I would say, but you don't end up with a 50% adder on top of a CMOS node. You end up with significantly less than that. It varies from node to node. It varies from process to process, but somewhere between 20 to 30 or 40% more than CMOS is typically what we would see.
Okay, great. I think we've run out of time, so I'd like to thank Simon for a great presentation and GlobalFoundries for sponsoring today's webinar. You can find out more information about their processes on their website. Please note that this webinar has been recorded and will be available to watch within about an hour from now. You'll find it in the events section of the Microwave Journal website. If you or your colleagues would benefit from watching it, please let them know. And we thank everybody for joining us today.
All right. Thanks again, everybody.